Hey guys, it is time to take a look at topic 8.2, some further revision questions. Okay, first things first, let's take a look at number 66 here. So, total radiated power arriving from a sun at a planet is 2.82 times 10 to the 17 watts. The orbit of the planet around the sun has a radius of 1.23 times 10 to the 7 meters. There's some issues with this problem. So I'm assuming here for part A that the total radiated power of the star is 2.82 times 10 to the 17 watts, not the total power arriving at the planet, because that would be super enormous. So slightly changing the problem for my solution here. So for A, we calculate the solar constant. This is the amount of energy incident on the planet as power divided by area, and area is given, of course, by 4 pi times the distance from the star to the planet squared. Okay, so we plug in our numbers here, and we get this value 148 watts per meter squared. Next, for part B, we're asked to calculate the average intensity of radiation radiated away from the planet in all directions. So in order to figure that out, we have to treat the planet like a black body, okay? So we're assuming here no greenhouse effect, no greenhouse gases, and if our planet is behaving as a perfect black body, in other words, it's radiating away all of the intensity, it's radiating away all of the energy that it receives, then this is the equation that we use. So intensity, average intensity is equal to the solar constant that we calculated in our previous equation times 1 minus the albedo, 0.22. And that will give us 148 watts per meter squared times 0.78, giving us 115 watts per meter squared incident on the planet's surface. Okay. 67. One of the planets in our solar system receives solar radiation with an intensity of about 15 watts per meter squared. Calculate its distance from the sun and hence figure out which planet it is. So I'm just using the same equation that we've used before. Note that this equation is not in your data booklet. So pretty important to make a note of it because it may come up at a later date. So the equation that is in your data booklet just says intensity is equal to power divided by area. So if you don't know the area of a sphere, if you don't know how to calculate the surface area of a sphere, that's going to be a problem. All right, anyway, if we know this equation, then it's fairly straightforward to rearrange it such that D is equal to the square root of power divided by 4 times pi times the incident radiation. Okay, the power then is the power of our sun, which is about 3.6 times 10 to the 26 watts. Divided by 4 pi times 15 watts per meter squared. And we get then a radius of about 1.4 times 10 to the 12 meters. Note that the problem does not actually give us this value. So you would have had to have looked it up as I did. I just went out onto the internet and I looked up the sun. I used Wikipedia, which is fine because this is not academic research. I just needed a quick figure. Okay, 2, next thing you need to do, and again, this requires a certain amount of ingenuity on your part, not fart. You need to find a table of planetary radii, okay? So I found one that gave the radii in astronomical units, which I then actually had to convert to meters, which was a little bit annoying. So you may have had to have dug around a little bit to find the actual planetary radius in meters. But that's part of the deal. I wanted you to do that. So Saturn matches this particular radius. If you have any questions about what I did, please don't hesitate to ask. I'm happy to share my work. Okay, 72 planets are orbiting a distant star. Planet A is 100 kilometers from the star and receives an intensity of 860 watts per meter squared. Yada, yada, yada. What is the intensity received at planet B if it is further away? Okay, so should be pretty obvious from the setup here that we have a proportionality problem where the total energy in the system is going to be conserved, and therefore we can use a proportionality. So the proportionality I've set up looks like this. First, intensity will be inversely proportionate to distance squared, which makes sense. This is a relationship that comes up in physics quite a lot. Okay, once I have that information, then I set up my equation, as you can see here, and I solve for the intensity at planet B, and conveniently, the intensity at planet B is going to equal the intensity at planet A times the squared quantity of the distance to A divided by the distance to B. Okay, so I plug in my numbers and I get 600 watts per meter for my answer. Very straightforward. Note that I did not bother including my units here because they're going to cancel out. So normally I might write my units, but this is not one of those times. If something's going to cancel out, it would just be a waste of time. Okay, number 71, I included a couple of equations here from the Hodder text, the orange textbook in my room that you do have access to. The thing we need to note, just starting out here, is that instant power will equal radiated power, okay? So these are the equations that are implicit in that statement, and it's not, this equation is not in your data booklet, so you probably want to make a note here. I recommend making a note. Okay, so in this case, the text gave albedo as 0.3 for planet Earth, and it also gave emissivity as 0.61. Sorry, that's not super clear there. So it's important to identify those variables as I've done here. And I also identified a couple of additional variables where A sub D is equal to disk area and A sub S is equal to sphere area. Remember that the radiation incident on a planet is going to be the amount of radiation falling on a disk, and the area of that disk is given by the planet's radius, okay? However, that radiation is then distributed across the surface of the planet, and the surface of the planet has an area of a sphere, okay? So, the math here is fairly straightforward after I plug in some values. Note that the radius of the planet actually cancels out, as does pi, and that's pretty convenient. Okay, once I get to this equation down here, I solve for temperature, and it looks like this. And I've done a little bit of intermediate math along the way just to get this value, 0.305 times S. Remember that S is the solar constant. Okay, so we have 0.35 times the solar constant divided by the Stefan-Boltzmann constant, which you should have in your calculator, probably. I plug in my numbers and I get 292 Kelvin. Okay, so this, in theory, should be the temperature of the Earth if we change our emissivity and albedo by factors of 10% respectively, which I've done here when I was setting up the equation. So you can see albedo, 1 minus 0.38 times 1.1 and 0.9 times 0.61. So that's where I modified those values as required. I should have pointed that out earlier. Okay, so there is number 71. 72, we are asked to calculate the solar constant for Uranus, or Uranus if you prefer. No jokes about Uranus. Okay, P is equal to 3.8 times 10 to the 26 watts. That is given, oh, that's interesting. Seems I used a different value earlier. Let me double check that. Yeah, I did. Okay, you might want to double check the power output of the sun. I may be using slightly different numbers here, which is not cool. I will fix that in the final version of this document. Okay, so for A, we are asked to calculate the solar constant for Uranus. So we use a formula for that, which is given by this value. Again, make a note. We plug in our values for the power radiated by the sun and the distance to Uranus. And we get then this value 3.6 watts per meter squared, which is much, much smaller than Earth's solar constant. Okay, we then calculated surface temperature, and we use the same values that we used previously. And here you can see, so in other words, for albedo, we use 0.3, and for emissivity, we use 0.61. And I'm kind of moving fast through the math here, as you can see, but when I solve the equation for temperature, you will get this value, and we plug in our numbers, and you will find that the temperature of Uranus is about 65 Kelvin. Its actual temperature is about 10 Kelvin smaller than this value, which probably indicates that it has a different value for both albedo and emissivity, which would make sense because it's a totally different planet. So not really surprised there, but this is pretty good rough work. We're only 10 Kelvin off, which is interesting. So we did have to make some assumptions here, and that is okay in physics. Sometimes you have to do that. All right, 73, anything important here? First thing, 73 has a mistake where you're asked to estimate the surface temperature of the star. Well, we are missing information if we want to do that. So what we actually need to estimate here is the surface temperature of the planet. That is a mistake in the text. Okay, so the assumptions that we're making here, again, are just that the emissivity and albedo would be similar to Earth. So these are my two assumptions right there. Okay, I then find the solar constant for this particular planet, and I find that it's about 142 watts per meter squared. Once I have that, then I can find its temperature. So I really need that solar constant in order to set up this equation, which I've now used a couple of times here. Okay, so I solved my equation for temperature, and again, you can see here that the areas for the disk are going to cancel out, although that 4 will remain there from the sphere. Okay, so we then get this simplified equation, and now it's a simple matter of plugging in our numbers, and we find that our new planet has a temperature of about 163 Kelvin. And they ask a question that is actually way outside the scope of IB physics. Do you think there could be life on this planet? Well, that's actually a very tricky question because it depends on what assumptions we make about life, okay? So if we assume that life on the planet generally looks like the life on Earth, then we would have to say it's way too cold for Earth-like life. Liquid water cannot exist at this temperature. But, big but, there may be other kinds of life in the universe, or even in our solar system. So there's some stuff we don't know there. For 77, I don't think I'm going to lecture through here because it's largely review and just kind of rearranging some fairly simple equations. So I think that you should be okay working through it on your own, but do check your answers. And as usual, if you have any questions, do not hesitate to ask. I will look forward to them. Here are the answers in the back, and they should pretty much match mine. And there you go. Okay. Right. Gentlemen, have a good day.